been doing with the derivative with limits. And similar to when we first talked about the limits, I did want to review the alternate definition of the derivative using limits, and then kind of see how this connects to some stuff that we already did. So to remind you, the alternate definition of the derivative at a is the limit as x goes to a of f of x minus f of a all over x minus a. And basically, when you're looking at it, how it works is we know that that means the derivative of a. Like this, when we see that limit expression, we need to interpret that as a derivative. Visually, what's happening, again, to remind you, is we have some x value at a and some at x, and the limit says that x is approaching a, so we have a secant line that is turning into a tangent line. That idea is kind of important. What's more important is that you recognize this statement as the same thing as f prime of a. So how can we use this? For some limit problems, if you recognize it as a derivative, you can actually evaluate it using your derivative rules. So like this first one, I have the limit as x goes to 3 of this 2x minus 8 all over x minus 3. Normally when you evaluate limits, you can plug in the top and plug in the bottom doing our direct sub. Well, 2 to the third power minus 8 is 0, and 3 minus 3 is 0. So we do end up with 0 over 0. This one, though, is not one that you could solve in Unit 1. Like, there's no factoring you could do. There's no rationalizing. Like, you're just kind of stuck with how it's written. But what you can recognize is that this statement is the alternate definition of the derivative, which I'm going to rewrite up here. So we have the limit as x goes to a of this f of x minus f of a all over x minus a. So you can kind of tell that this is the derivative of the function 2 to the x at the value of 3. So this limit expression means exactly the same thing as f prime of 3 for 2x as your function. So instead of finding the limit the old-fashioned way, we can just use our derivative rule. This is one of the rules we covered yesterday, the natural log of 2 times 2 to the x. And so then I can plug this in. This limit is the same thing as the derivative at 3. Well, the derivative at 3 is the natural log of 2 times 2 to the third power, our 8 natural log of 2. So that is the answer to the limit, and we can use the derivative to get to that answer. Questions on that problem? All right, sometimes we have the alternate definition that looks like more of a question in disguise. Here's another limit question that is a little bit hard to do using methods that we have already learned. So again, you could do direct substitution, but if I'm doing the limit of tangent of x, the tangent of 0 is 0, and of course x is just going to be 0. So you have the indeterminate case, but this doesn't look like the alternate definition right now. But we can kind of force it to look like the alternate definition. I'm going to rewrite it over here, a little bit more space. And the reason we can force it to be the alternate definition is I see that x is approaching 0. So if I treat that like my a value, well, the tangent of 0, f of 0 is 0. We can see that that limit expression ends up being the same one. It really is the alternate definition in disguise. So we can interpret this limit expression means the same thing as the derivative at 0 for the function of tangent of x. If you're evaluating this limit without derivatives, you would have to use a lot of like some trig identities and eventually like L'Hopital's rule is what you could do as well. But we can do the derivative using this one. We know the derivative, this is one of our rules. F prime is secant squared of x. Again, this limit expression is the same thing as f prime of 0. Well, f prime of 0 would be the same thing in this case as secant squared of 0. our 1 squared equal to 1. So again, we can evaluate these limits using derivatives when we recognize it as the alternate definition of the derivative. Questions?
Why can't you just add the zeros to it?
I mean, short answer is because it's just 0, so we're not really changing the problem. Like if I was trying to force the alternate and I had to do like -2 on the top and the bottom, then that wouldn't be something that I could do because then I would be changing the problem. But subtracting by 0 is not changing it. So I was mainly just doing this to like prove that this limit really is just the alternate definition of the derivative just simplified. Like we just didn't write the zeros there to see it.
Mr. Brown,
Yes.
if there was another number, would you do tan of x minus f of a x minus a? So you would use that number?
Yes, but again, this one, we're gonna have to do it, the derivative at 0, and the reason we have to only do it at 0 is because of that portion of the limit. So
No, I'm
in the
saying
alternate
if
version of the
x,
definition, like x goes to 0 means that's gonna be the derivative at 0.
I'm saying
if I want to
f
fill
x
in-
approached like 5, would you do tan of x minus f of 5, x minus 5?
So yeah, like if I wanted to write it in the derivative, so if I wanted to say, well, what's the derivative at 5? Like clearly we know the derivative, so we can say just, okay, it's gonna be the secant squared of 5, but the limit notation of that would look like x goes to 5, tangent of x minus the tangent of 5 over x minus 5. So yes, we could take any derivative we know and technically write it as a limit.
Okay.
That one becomes a pretty messy one to solve by hand. So that's why it's good to know the derivative rules to kind of translate a limit into a derivative. So that's the alternate definition. We know that we also have the traditional definition of the derivative. It's the ones that are all the plus h problems. So we have h is going to 0, and it's the f of a plus h minus f of a all over h. Conceptually, what's happening is the gap between 2 points is this distance h. That is the change in x. That's going towards 0. And then when that gap is going to 0, then the secant becomes a tangent. What's more important, though, is when you see these limit questions, is you can identify where you're taking the derivative at, and then also you can identify the function you're taking the derivative of. So an example of that would be this first one. I have the limit as h goes to 0 of the sine of pi over 2 plus h minus 1 all over h. If you're evaluating that limit by hand, you would have to do like some sum and difference identities and kind of work your way to an answer. But what we can also recognize that this is the traditional definition of the derivative. There's the a value, so this is the derivative at pi over 2. Well, what function is a plus h being plugged into? It's being plugged into the sine of x. So that limit expression means the exact same thing as f prime of pi over 2 for the sine of x. Well, this is one of our derivative rules. The derivative of sine is cosine, so I can just evaluate the limit using a derivative. You will see that there are some problems that you probably can do it like the old-fashioned way, like in Unit 1, but I think identifying it as a derivative makes it a little bit quicker for us, and that would be this example. So I have the limit as h goes to 0 of this x plus h cubed minus x cubed all over h. So like if you're doing that by hand, you would have a bunch of foiling and distributing for that term. Hopefully things will cancel out, factor out the h, and cancel and plug in. Or the quicker way is, oh, I know that that is the traditional definition of the derivative. There is no a number plugged in, so that's just asking me to find the derivative at x for what function. What function was plugged in to the x plus h, and it appears to be something cubed. So the function I'm actually taking the derivative of is x cubed. Well, what is the derivative of x cubed? The derivative of x cubed is 3x squared. So we recognize that this limit is the same thing as f prime, which would give you 3x squared. I'm not going to work this one out fully, but again, if you did that one the long way, like we did in Unit 1, you would see that after you plug in h for 0, you would be left with 3x squared. Questions?
Why is that first value x?
That first value is x because we know typically the numerator for the traditional definition is this f of a plus h minus f of a, where a is like the number you're taking the derivative at. And in this case, we don't have a number there, it's just kind of being replaced with x. So we're really just finding the derivative overall instead of at a certain value. So where this becomes nice for us, this is going to be my last slide of notes to kind of pull it all together, is I have 3 limits here. 2 of these you could do the old-fashioned way. Like that first one, I think most of you can look at that and say, oh, factor and cancel and get to the answer, which is easy. But I also want us to be able to recognize when we're looking at a derivative and when we're not looking at a derivative. So like this first one, this is not h is going to 0, so this is definitely the alternate version of the definition of the derivative. The second 2 are definitely more of the traditional definition of the derivative with the h. And for each of these, we can kind of do them pretty quickly by first identifying the function being plugged into them, the value we're taking the derivative at, and then instead of evaluating it like a limit, we can evaluate it like a derivative. For example, in this first one, I think the alternate one is nice because it clearly shows you what your function is and clearly shows you what your a value is. So this first one is the same thing as saying find f prime of 4. What is the function being plugged into that? X squared. What is the a value? 4. We know that f prime of x would be 2x. Plugging that into the derivative, 2 times 4 gives you 8. Just for the sake of comparison, so in Unit 1, instead of using this like a derivative, we would have treated this like a factor and cancel problem. So you can factor the numerator, factor the denominator, cancel, you're left with x plus 4, x is going to 4, 4 plus 4 is equal to 8. So you get to the same answer. This one honestly is probably just as easy to factor and cancel, but I want us to see the connections between of like, oh, this represents a derivative, so that limit is actually calculating the slope of a tangent line. So we can add some meaning to those limits. The second and the third one are both the traditional definition of the derivative. So for the traditional one, you have to kind of figure out what function is being plugged into. And then you also need to figure out what that a value is. So we can see for that second row, the a value appears to be 9. The function being plugged into it is x, and the a value is 9. That's where that square root of 3 is coming from. So we have minus f of a, f of the square root of 9. That's going to give you 3. So if that is my function, we can find its derivative. The derivative would be 1/2 x to the negative 1/2. And I can go ahead and plug in my a value, 1/2 on the square root of 9, which is going to give me 1/6. The longer way to do that problem, you could rationalize. And then you're going to have to simplify, and then hopefully something would cancel out. And then you can do your direct substitution. So again, that is how I did some of the problems quicker in my head. In Unit 1, like I knew and recognized certain problems as derivatives, and I can do derivatives a lot faster than limits. But again, that kind of shows you the connection of what you're finding. And then this last one, the function that you're using, we can see that the x plus h being plugged into it is the secant function, a negative secant function to be clear. The a value is pi. We can check that because the negative secant of pi is going to give you a positive 1, so it does check out. The derivative of negative secant, so negative is a coefficient. the derivative of secant is the product of secant and tangent. So if I want to find the derivative at pi, I can plug it in. If you need the reminder of the unit circle, pi is over here. So I have the negative, the secant of pi is -1, the tangent of pi, sine over cosine is 0. So we also have a derivative of 0. That third one is really the only one where knowing that that's a derivative would help you out, because there really isn't a short way to do that one algebraically. So again, I don't really have any homework attached to that. That's more of just like a conceptual thing that I want you to see. Also kind of we started this class with limits. We've now learned derivative rules, and we can always connect these back to limits. Questions on that page?
Is this stuff gonna be in the test?
I don't have any questions like this on the test, but it does show up again later, like in other units, if that makes sense.
Yeah.
And I guess you do need to understand what could be on the test is some similar stuff that we saw at the end of Unit 1. Like that first column you see, I need you to recognize that that means the derivative. That would be something that I expect you to know. So being able to at least recognize when a limit is representing a derivative and when it doesn't represent a derivative. So that is where I am going to kind of end today's notes. Again, tomorrow there is